So now that you've learned what a semaphore is conceptually and you've got a better understanding of its structure and functionality in Java, we talked about some of the key methods, let's talk about ways in which you can apply semaphores in practice. And there's a couple different ways. The first way, which is what we're going to talk about here, is how to use a semaphore to mediate access to shared resources. And then the next part of the lesson, we'll talk about how you can use semaphores to coordinate interaction between threads. So this particular example is going to be driven by the Palantiri simulator, which is your assignment that you're doing throughout the course. And we're going to talk about how semaphores can be used to help with that particular type of concurrent resource management scenario. So this Android app, which you're implementing, shows how a Java semaphore can be used to limit the number of beings from Middle Earth, like Gandalf and hobbits and Aragorn and the Dark Lord himself, who can gaze into a Palantiri concurrently. And as you've no doubt noticed from your assignment, each being is implemented to run in a separate thread. The app can be configured to restrict the number of beings that can currently gaze into a Palantir. So let's say we have 2 Palantiri, and we don't want to let more than 2 beings gaze. And why might you do this? Obviously, this is just a whimsical, fun example that you can visualize. But in real life, you might want to put a limit on the number of things you are going to allow concurrent processing for. And that might be, for example, let's say you have a quad-core processor and you don't want to let all the cores be used because then other things in the system will be non-responsive. So we're going to limit the number of resources that can be used concurrently at any given time. So in this case, we're going to have a semaphore with a count of 2. And the way that the protocol works is a being must acquire a semaphore, which is pegged to the number of Palantiri, before it can begin to gaze. So you can't start to gaze until you've got yourself a Palantiri or a Palantir, and we use a semaphore to make sure that we don't try to dole out more Palantiri to threads than there are Palantiri that we want to have in use at any given time. So we use a semaphore to atomically acquire a permit, which will decrement the permit count by 1, and thereby grant access to the thread as long as the count is greater than 0. At this point, let's say that Gandalf wants to talk to Sauron. Doesn't actually occur in the book, but I suppose it could in theory. So in that particular case, those 2 beings have got their Palantiri, they're gazing at them, the count is 0, and if anybody else comes along, like hobbits or elves or dwarves or men or whatnot, they're going to end up having to wait until Sauron and Gandalf finish their gazing. When a thread or a being is done, it's gazing, it releases the semaphore and gives back the Palantir. Now, this is very important to understand, and when you think carefully about the design of your Palantiri manager that you're doing, and you'll do lots of them over the course of the semester, we have 2 different things we're keeping track of. We're keeping track of how many Palantiri are available at any given point in time, and that's what the semaphore is used for. And then we're also keeping track of specifically which Palantiri are available, and that's what the hash map is there for. And the semaphore is just used to mediate access to the concurrent resource management internals. And the spin lock is used to make sure that when a thread is granted access, that it doesn't end up corrupting the shared state, which is the hash map itself. So the hash map, which is otherwise unsynchronized, is protected from concurrent access by the spin lock. And later in other assignments, you'll replace it with other type of synchronizers. And that's used to make sure we don't have corruption of the hash map, but the Palantiri manager uses a semaphore in order to decide who gets to even get into the critical section to check whether there's available Palantiri, or which Palantiri are in fact available specifically. So those are 2 distinct things, and they're protected in 2 distinct ways. One with a semaphore, one with a spin lock in this particular case. And once someone is given back the Palantiri or Palantir, then another being can detect that the semaphore is now greater than 0, as it is here, and then that could go ahead and grab the Palantiri and gaze into it and decrement the semaphore count by 1. This particular example fully brackets the acquiring and releasing of permits. In other words, the thread that acquires a semaphore is the same as the one that releases it. That's not always the case, as we will see next. Here's a little UML sequence diagram that shows how all this stuff works. It's kind of fun. So we've got a Palantiri thread, which is going to start a bunch of being runnable threads. This is kind of what's going on in your program. And then those things are going to get access to Palantiri, and then they're going to use the Palantiri manager to mediate access to the fixed set of Palantir objects. So here's what happens. We start the main thread. This is what's done for you by our framework. You never do this. You then go ahead and start up a bunch of being runnable threads. That's what you're doing in assignment 1A, or that's what you did in assignment 1A. So they start to run. And when they run, as you can see here, each of these threads is going to block or going to try to acquire a Palantir. And those calls under the hood are going to use your implementation, right? They're going to use the semaphore stuff and the spin locks and so on. And let's say, just for sake of argument, we only have 2 Palantir available, which is consistent with our use case here. So these 2 threads, in no particular order, well, I should take it back. They will go in a particular order. Whichever one gets there first will be the one to get the Palantir next, because we use a fair semaphore. And that means that they're queued up in FIFO order, first in, first out order. So let's just assume that these 2 threads start up. They both acquire the Palantir. This thread, the one that's red, doesn't, so it's blocked. Those threads can now go ahead and gaze for some random amount of time, fixed but random, as we say. So they're off gazing. This guy's still blocked. And then when they're done, they release the Palantir that they're gazing, which makes it available. And then this thread can then grab it. And since we do this fairly, they take turns, right? So if this was not fair, then a thread that released the Palantir could turn around and reacquire it right away, which would not be fair, right? There are situations, of course, where we don't care about fairness, but in this case, we're trying to be fair. We're trying to give each being an equal shot. And when it's its turn, it's its turn. So this guy can then go ahead and run. He can gaze. And when he's done, he'll release the Palantir as well. And then other Palantir to be acquired and gazed at by other threads. That kind of is a walkthrough of the steps involved concurrently and what's happening under the hood. So that's the end of the overview of mediating access to shared resources using a Java semaphore.